So we've learned a lot of tools, terminologies, expectation, tail inequalities. So imagine we have all the ingredients like flour and sugar and jaggery and cashew and so on, and we're going to make cakes out of them, right? Some sweets and cakes. So in particular, we want to see how to use all these tools for expectation analysis in algorithms. So let's start with, okay, so I'm going to say, let's start with finding max. So this is the first problem we saw yesterday. There are actually some empty chairs. People can come closer. Yeah, so remember how the algorithm worked. We want to find the maximum of a list of n numbers. So what did we do? We said we created a variable called max. We initialized it to the first element, and then we had a for loop. Which said if ai is greater than max, then we update max to ai, and finally max will have your maximum element, right? So you can translate it to any of your favorite programming language. Okay. So now let's say I want to do some average case. So we saw in the worst case, the algorithm made n minus 1 comparisons. Okay. So I want to do some average case analysis. So how do I go about doing it? Right. So the first question is average over what? When you say expectation, and must be some randomness, some average. You are talking about average over what? So first question, what is? I mean, suppose I want to know this algorithm's performance on the average. Then what is it? Average over what? Right. So many of you probably know that Quicksort, for example, its worst case complexity is n square, but it is n log n on the average. What does that mean? Average over what? Yeah. No, the number of comparisons is what we are counting. So we said the number of comparisons in the worst case is n minus 1. But now I want to say, what is it on the average? So average over number of experiments. Okay. Yeah. Okay. So what are our experiments here? Different arrays. Okay. So that's a starting point, right? Different arrays. You have another array of n input, and I want to count the number of comparisons. Another array of n input, count this. So now I want to know the average over all possible input, right? But the problem is there are infinite number of inputs. You change your values, right? I mean, many of you probably have seen this in the context of Quicksort, but maybe never asked this question: average over what, right? Because there are infinite number of input. So what does it mean by average over all possible inputs?
Different kinds of input.
Different kinds of input. Okay, what is the kind of input?
Maybe in a sorted array, unsorted array, different kinds of input, not the different types of input.
Okay, so something is now bringing in. Okay, so different kinds of input, different. So anybody else wants to add to that? So for example, let's say I want to find the maximum of and here is another algorithm, another input. Right? These are different input, but they are not different kinds of input. Why? What is similar about these two? Both are sorted. I see. Okay. The maximum element is found at the same place. So, in the context of sorting, in the context of finding max, whatever. So, let us say now suppose I write a different sequence of input, not necessarily sorted. Now, are they same kind? They are not sorted necessarily. So, one is a multiple of that. See, that's not really, I mean, we are doing comparison based algorithm. Okay. So, the algorithm, all it's doing is comparing elements and then figuring out the answer. Okay. In the context of this comparison based algorithm, these two inputs are same because equal size. No. Why are they same? I mean, there is something about these two inputs which makes it similar, which makes the number of comparisons the same. What is the commonality about these two inputs? Huh? Number of elements, I am going to stick to n because I think it makes. Okay, that's what she said. Maximum is at the end, and you're saying maximum and the largest minimum are at. There's something common about. Okay, if we sort both the arrays, the indices. So, for example, here if you say 1, 2, 3, 4, 1, 2, 3, 4 would be the sorted order. Here it would be 1, 2, 3, 4, then 1, 3, 2, 4. So, what is this? So, I am looking for a word. Permutation. The permutation of the input. If you take these n elements, if the permutation, so if you, for example, the sorted order, if you take the sorted order permutation, if these two are the same, then the algorithm's performance will be identical. Okay, you can verify that whether it's a question of max finding or sorting, because the algorithm never even looks at the number. If you think about it, if you see the algorithm, whether this algorithm or merge sort or heap sort or something, until the end, the algorithm may not even know what is AI, right? Whether it's 2000 or 52,000 or 273, the algorithm may not even know. But what will it know? It will know that that element is smaller than this, bigger than this. So all that matters is the permutation, right? So, we are going to now analyze this algorithm under this assumption. So, because when you want to do expectation random, there must be some randomness. So, what is the randomness? I am going to say, assume your permutation, input permutation is random. Okay. So, what does that mean? There is a uniform distribution. So, you can think of it as, on this permutation, this algorithm performance is this. On another permutation, the algorithm's performance is this. Another permutation, the algorithm's performance is this. And now I want to take the average. That is the average performance. Okay. So now let's come back here and say, what is the average number of comparisons made by this algorithm, the max finding algorithm, under all permutations? Okay. This is a trivial question. Then we will get into more interesting question later. Okay. This is really a trivial question. So you should be able to tell me. So what is, how many comparisons are made by this algorithm for any permutation? This is interesting. For any permutation, it's n minus 1. For any permutation, right? So what will the average be? N minus 1, right? If all the marks are the same, what can you say about the average mark? It will be the same, right? So, in the case of this particular algorithm, in the case of the number of comparisons, it doesn't, because it doesn't depend on the permutation. It's always n minus 1, because if you see the way we are doing, right, this step is the comparison step, and it's always taking your AI and comparing it. So, it doesn't matter what permutation you give, it will be n minus 1. So, average really doesn't make a difference. But where does the average make a difference? Let us look at this step, which we did not look at carefully yesterday. This step where the max value changes. Okay. Imagine we had this initial max, and then when I make these comparisons, this max value changes. Now, can you tell me what is the worst case of how many times this step will be performed? But that is worst case. Here it is not always, right? Because for a different permutation, that number will change. Now, it makes more interesting to ask what is the average. Do you see? So, the next few minutes, let us do a careful analysis of average number of this step. Let us think of it as swap. Max is swapped. Max is a variable which starts with A0, and every time some bigger element comes, it changes. And I want to know, because this in the worst case is n minus 1, but it is not n minus 1 all the time, right. So, what would be an example where the worst case happens for this step? Okay, there I got two answers. Let's see. So, what she says, when the maximum is at the end, and the other answer says the max when it is sorted. So, let us say I have the maximum is at the end. Will it really make, how many moves will it do? 2, right? Because initially you initialize to 7, and only at the end it gets moved. So, this is not really the worst case, but what would be a worst case is if it is something like this. No. If the input is something like this in increasing order, every time the max will get changed. Okay. So, we have this extreme thing. Suppose if the max is the first element, then how many times will you change it? Yeah, or maybe 0, right, because you initialize it and then you never change it. So, we have this extreme case for some permutations, lots of permutations. Wherever you have max at the first location, it does not matter what the remaining permutation is, the number of times max will get changed to 0. And there is a permutation like the sorted permutation where the max is equal to n minus 1. So, now we have a variation. It makes more interesting question to ask what is the average. Now, you know what you are trying to find the average of, right? It is the average over all permutations now. Okay. So, now we can talk about expected number of x, where x is the, let us say, number of swaps. And this is the question we want to ask, and whenever we talk about expectation or average, should be clear about what is this random experiment you are doing, expectation over what. Here we are doing expectation over this permutations. Okay, they are all uniform, every permutation is coming and there is this different number that comes out as the number of swaps, and I want to know what is it. Okay, so this is what we want to analyze. Okay. How do I go about doing it, right? So, let us break it up into small steps. So, let us say let xi be the event that ith element gets swapped. it comes into the max. So for I greater than or equal to 1. Okay, initially max is set to 0 and there are n minus 1 other things that happen, and so at the back of your mind, if you are one of like me who are comfortable with doing these averages, think of it as we are doing this for every permutation. In fact, it may be very useful to do some small example. Take all permutations of 3 elements and find this number and do the average. Okay, and that's what we are going to do it in a for general case. Okay, so I want to say what is the event that the ith element gets swapped. Now, can somebody tell me what is E of x? What is this? What is x? X is the number of swaps at the end. Can you say it in terms of xi? Summation over xi, right? Because x is a random variable, xi is a random variable. So x is simply summation over xi, because x1 is swapped plus x2 is swapped plus x3 is swapped, and we know linearity of expectation. So this is basically E of summation over xi, I going from 1 to n minus 1. Okay. So now we are done. If we can figure out what is the expectation. So this is, we are done if we can figure out what is expectation of xi. Right. So what is expectation of xi? Well, it is the probability that ith element will be swapped, right, into 1 basically, because if it's swapped, it's an indicator variable. If it is swapped, it will add 1 to the number of swaps, otherwise it's 0. So it is the probability that, so xi is 1 if ith element is swapped. Okay, I'm overusing this term xi. I'm saying it's an event, it's also an indicator variable. Hopefully there is no confusion. Okay, so now all we are left to do is that I have this random permutation. Keep that at the back of your mind. What is the probability that ith element is swapped? Well, when does that happen? You are reading this and you look at this AI. When is this going to enter your max? If that element is greater than, that element is greater than previous. What does that mean? Yeah, all the other elements. It is the largest in this first I positions, because the previous max is basically max for the previous thing. So this is the probability that AI is the largest out of A1 to AI. Right? Now remember, it's a random permutation. We are talking about running over all possible permutations. Let's do this probability analysis. So what is the probability? So now your 1 to I is another random permutation. Okay, that's another easy thing to check on this I things. And what is the probability that my ith element is the smallest out of it? Any guesses, or you want to do the calculation? Okay, I mean, nothing works. You can just do some brute force calculations. Okay, you know the probability is some numerator by denominator, right? So what is the denominator? All permutations. So n factorial. Okay, so this is the question. Among all the permutations, well, there are n factorial of them. What is the probability that the ith element is the largest of the first I elements? That's a question, right? So denominator is n factorial. I mean, there are many ways to figure this out, but let's do it in a very formulaic way. Now, the first I elements can be any of the I elements. Okay, so you have so many choices. How many choices? Yeah, NCI, right? N choose I. Yeah, N choose I for the first I elements, and the first I elements can be in any of the I factorial permutations. Well, no, not any of the I factorial permutations. What permutations are allowed? Because I want ith element to be the smallest. So, how many permutations are there? Yeah. Out of the I factorial permutations, which I am allowed for the first I locations, the ith element is supposed to be the smallest. Yes? Somebody said it, yeah? I minus 1 factorial permutations. And the remaining n minus I elements, I don't care, and whatever permutations are all possible permutations. Okay, I mean, when in doubt, this is a very crude way of finding it. There may be other nice intuitive way of figuring it out. If you do all this calculations, you will see that it will turn out to be, if I didn't make any mistake, it will be 1 over I. Yeah, right. This n factorial will cancel out with this n factorial, and that I factorial in the denominator will have one I coming here, and the I minus 1 factorial will cancel out. The n minus I factorial in this term will cancel out this n minus I factorial. But you can think intuitively, okay, there are I terms, what is the probability that this will be the smallest, 1 over I? But sometimes it can be very misleading. So I find it comfortable to just do this brute force calculations and convince yourself. Okay, good. So now we are done, right? We are done. So what is our expected number of moves? Well, it's here. So this is what we want to compute, and we know what is expected because xi is a 0 1 variable. So what is the probability that it's 1? Well, we already checked, it's 1 over I. So summation 1 over I going from 1 to n minus. Okay, this is also can be written as harmonic. This is just a symbol for Hn is summation 1 over I 1 to n. Okay. But we are not happy with a term like this. We want to know big O of what, right? This is not what you expect. So what is big O of this? Do you know? This is, anybody knows the estimate for this? Clearly much better than n, right? Because summation 1 is n, right? But this is like 1 over I, 1 plus half plus 1 over 3. Okay. It turns out you can do it in a tutorial exercise that Hn is big O of log n. Basically, there are many ways to do it. You could draw this curve y equal to 1 over x. Okay, the curve will look like this, and then the area under the curve is an integral function, right? You can just say integral whatever with your limit boundary terms 1 over x, that will be like natural log of x with the boundary things. And you can say that that area under the curve pretty much nicely bounds the summation 1 over I, because you can draw some vertical strips of rectangles of area 1 over I, and so the area under the curve will be like an upper bound on summation 1 over I. Okay, I pretty much gave you the proof, but just need to work out the details, and that's an exercise. Okay, good. So now what we have shown, it's a very, it's a very useful thing, that in your max finding algorithm, number of comparisons is always n minus 1, and this number of swaps in the worst case is n minus 1, but on the average is only logarithmic in n. Okay, this is on the average again means what? When you average over all permutations. If your permutation is a random permutation, you have an order log n bound. Okay, and we didn't do anything fancy except to analyze what is the probability that the ith element will be swapped. Okay, good. Now let's move on to the other problem which I wanted to talk about, and that's the finding kth smallest. So we saw a lot of algorithms in different models yesterday, right? You have this array for some k. I mean, ideally I want to find the median element. That's the k is equal to n over 2, but we'll design a recursive algorithm where this k will keep changing. So I'm going to say finding kth smallest element. When k is small, like 1 or 2, we know how to find the smallest, second smallest, third smallest. K is constant, we can do in linear time. But what I told you yesterday is that for any k, there is a linear time algorithm, which is one of the powerful applications of divide and conquer algorithmic technique. It's about 1-page algorithm. It requires about 1 lecture to go through it with some understanding of the recurrences and so on. But what we are going to do is sort of design a much simpler randomized algorithm, okay, and argue that the expected running time is linear. Okay, so that's our goal. Okay, so the algorithm works like this. It's sort of like quicksort. Okay, pick some pivot element, some element in the array. Step 1, compare all elements with x. Okay, so let's for ease, let's assume that all elements are distinct. This is not a serious assumption, but it makes the algorithm and the analysis cleaner. So I'm going to make that assumption. Okay, so I'm going to now compare all elements with some element I picked. Let's call it x, and I have a counter which tells you how many are smaller, how many are bigger. Okay, so let's say and suppose r elements are smaller. So this is something I have a counter which every time when I run through this comparison, if the element is smaller, I will increment that counter and I compute this RAM. Okay. If r is equal to k minus 1, what can you say? Yeah. I'm looking for kth smallest element. X is the kth smallest element. You're done. You can stop. right? There's nothing more to do. If you're lucky, I don't know. I just picked some element and I did this comparison, and I may be lucky that I actually got the kth smallest element. If r is equal to k minus 1, then done. Okay. Else, if r is less than k minus 1, so let's say find k a. That's my algorithm. In the array A, find the kth smallest element. Let me also add. So, not only in this step I am going to do a counter, I am also going to partition the input. Okay, that's also easy to do. Okay, let's not worry so much about space and other things. So, I compare all elements with x. Anything smaller than x, I put it in one bucket. Anything bigger than x, I put it in one bucket, right? So, let's call S and L. These are smaller than x and L is larger than x. Now, if R happens to be less than k minus 1, so I am trying to define a recursive algorithm. Okay. Where do I go and now recurse? In the L array, what do I look for? So, find in the L array, what do I look for? R is less than k minus 1. K minus R, exactly. Is everybody with me on that? So, what she's saying is, you've done this partitioning. There are some R elements to the left of x and R happens to be smaller than k minus 1. I am looking for kth smallest element. Okay. So, R is less than k minus 1. So, you take that R and add this one and it's still less than k, right. So, now in the right hand side, which is the larger element list, now my new task is to find an element whose rank is k minus R, right. Is it R or R plus 1? Okay, k minus R or R plus 1, right, because there are R elements smaller than x and then there is x. So, that makes it R plus 1. So, now in the right hand side I am going to look for k minus R plus 1. Else, what does that mean? R is bigger than k minus 1, right. So, now where do I recurse? Find in the small element, what rank do I look for? No, k. I want to look for kth smallest element. Remember, within S, within L, we didn't bother doing any ordering. We didn't make comparisons. All we did is compared everybody with x. These are smaller, these are larger, and let's say maybe it's useful to do. Let's say I'm looking for 100th smallest element, and if I have exactly 99 elements smaller than it, then good, x I found the 100th element. If I have some 40 elements smaller than x, then 40 and 41. So, I should subtract 100 minus 41, that is 59. Look for the 59th element in the right side, that is the first step. Or if I really have, I am looking for 100 smallest element, then 200 elements are there left less than x, good. Then look for 100th smallest element in the smaller side. Either way, I have reduced the size of the set where I am recursing. That is all the algorithm is, okay. That is all the algorithm. So, now let's write a recurrence relation for this algorithm, right. If I pick some element, I just said some element, So it's not yet a randomized algorithm. I picked some element, did some comparison. So how many comparisons are made in the first step? So if I write a recurrence relation and write this as T of n, how many comparisons are made in the first step? N minus 1, because all I did is I ran through the entire list compared with x, n minus 1 comparisons. And then what is left, I don't know. Either I have to recurse in the set S or in set L. How many elements are there in S and L? Well, I don't know. Okay, this is a challenge. I'm going to just say, I don't know, but in the worst case, okay. Now, what would be a bad case? X is some element. So, after this one round of comparisons, either you have to recurse in the smaller set or the larger set. I mean, smaller set meaning the set size is not necessarily small. These are elements smaller than x and elements larger than x. I am going to go and recurse. I don't know the sizes of this set. What would be a bad scenario in terms of the sizes of this set? Yeah, I can't. If x is the smallest element, for example, then there is nothing on the left side and everything is on the right side, and maybe I am looking for some 400th element or something. So it's, so then what would be the recurrence? N minus 1 plus T of n minus 1, because everything else remains, or yeah, because only thing I have removed is x, everything else is there. What is the solution to that recurrence? N minus 1 plus T of n minus 1. Well, let us keep expanding it, right? N minus 1 plus, I mean, if you are so unlucky that this kind of partition happens every time, then n minus 1 plus, okay, let us look at one bad scenario where, well, let me keep expanding it, right? T of n minus 1 is n minus 2 plus T of n minus 2. So, this will be n minus 1 plus n minus 2 plus n minus 3 plus n minus 4 plus dot dot dot, which is order n square. Not great at all, right? In fact, I can even sort in n log n time and pick my kth smallest element. Really didn't do a good job here. What would be a good case? Well, the good case is you already found the kth smallest element, you are done. But let us say in terms of recursion, suppose you are recursing, what size of L and S is sort of good? N by 2, n by 2, let us see, because remember, I am recursing, unlike quicksort, we will come back to quicksort later, I am recursing only on one direction. Quicksort, you do this pivot and then you recurse here and recurse here. Here I am not recursing in both places, either in L or in S. Okay. So, suppose if your x happens to be pretty good in the middle, so you have T of n equal to n minus 1 plus, let us say, T of n over 2, then if you know, if I even ignore the minus 1, so what is the solution to this recurrence? Again, keep expanding it. I mean, this is not the formal argument, you need to prove by induction or do some master theorem or something. But if I keep expanding it, what will you get? N plus n by 2 plus, and this will sum to? The first term itself is n. How can it be log n? N upon What is 1 plus half plus 1 by 4 plus 1 by 8 all the way? Yeah, what is the sum? What does it converge to? Which is? Yeah, work it out, It's just 2 minutes, right? So let's take n out. One plus half plus 1 by 4. And if you go all the way up to infinity, what is the sum? 2n. The whole thing is 2n. Essentially right, it's n plus n by 2. So it's linear. Linear is what I am aiming for. This is good. So if you partition it, if you are lucky and you picked your x somewhere close to the middle, you have a linear time algorithm. If you have picked closer to the extreme, you have a quadratic algorithm. Now this is a great test bed for us to do some randomization and expectation analysis. Right? So notice that it doesn't really matter n by 2. So if I actually make it n by 4, let's see what happens. Okay. So T of n, I even ignore the n minus 1. So what is this? N plus n by 4 plus n by 4 square, blah blah blah. So this is n into 1 plus, no, let's do 3n by 4. If I do n by 4, obviously it's going to be even better than n by 2. So let's do 3n by 4, and I want to say even this is good. So it's 1 plus 3 by 4 plus 3. This geometric series. What does this add up to? 4n. So it's just still some order n. Okay. So what is the point I want? Okay. So this is useful, that now let's just go back and randomize my algorithm. Right? I picked some element. Now what do I do now? What is the way to randomize this? So this is a deterministic algorithm, because the algorithm had no randomness whatsoever, right? So if I want to modify the algorithm to be a randomized algorithm, what do you think I should do? See, x, I don't know. Only after you do the comparison, you know whether it's x is to the extreme or x is close to the middle or something. Per se, I don't know x is. What is its rank? Okay. So I want to pick some random element x. Okay. Let x be, now I am going to say not some element, so first of all, what does this mean? Okay. Now, what does this mean? How do you actually implement it? People might have implemented randomization in an algorithm. What do you do? I don't know if you have implemented Quicksort or something. What does it mean by x is a random element? Right? You have random number generators. Computers can give you random number generators. So you have this n elements. You go and ask it to give a random number between 1 and n. It gives you 27, let's say. Then I just go and pick the 27th element in the list. That's all, right? So under the assumption that the random number generator gives you a uniform random number between 1 and n, that means I am going to pick a random element from this array, right? I have this array of n elements where I have to find the median. It picks a random element, and then the rest of the algorithm is the same. I do a count, compare the rank. Depending on the rank, I go on the left or right or stop. Now, this are random numbers now, because it's a function. So now we have the experiment. What is this experiment? It is either the pivot is the smallest or the second smallest or the third smallest, and we are the random number. If you believe the random number generated, then this is uniformly at random. So now I can slowly talk about probability. What is the probability that the x I pick is the ith smallest element? Yeah, so initially, if there are n elements, and you consult a random number generated between 1 and n, it gave you some number and you pick that index, what is the probability that that element you pick is the ith smallest element for some I? 1 by n, because it's a uniform probability, because I am not biasing, I'm consulting the random number generator and it picks me some number. So with now I can bring in, because now this is a randomized algorithm. So far the way I described, there was no randomness, there was no random experiment, and I just simply did some examples of what if this x happens to be the smallest element, then what will be the running time? If x happens to be the middle element, what is the running time? That's what we did, right? Now I have randomized this step. So now I know, now I can do the average. I can do all this, right? This was when x was smallest. And this was when x was, n by 2th element, and this was when x was either n by 4th or 3n by 4. So now I can, so I have a randomized algorithm. Algorithm is over, done, right? This is the algorithm, clean, complete algorithm. Just pick a random element, compare it with everybody, depending on the rank of that element, you recurse in this side or that side. That's it. That's the algorithm. Practitioner who doesn't care about analysis can take this algorithm and go ahead and implement it and happy about it. But as theoreticians, we need to give some sort of a performance measure of this algorithm. So we have to tell how good the algorithm is on the average, right? Because now it's a randomized algorithm, you can't talk about worst case. So we will talk about and the average, and average over what? But there is a random experiment happening. So average over all these random, the outcomes of the random experiments. What are the outcomes? Different x's, different pivots, right? This x, different x's based on the, so if x happens to be here, I know the running time. If x is here, I know the running time, and I need to do the average. Of course, I can, like I did here, one by one I can do and take this and compute all over. That's going to be a mess. Let's write one clean recurrence relation for the expected number of comparisons, okay. Now I am going to say, suppose Tn is the number of comparisons made. By the randomized algorithm. Then we want the expectation of this, right? That gives you the average performance, and the expectation is over all outcomes of the random steps that's being done. Okay. So we know, so the first step 1, there is nothing to do expectation, it is always n minus 1, because it just picks an element, compares with everybody and does the partitioning all the time. Yeah, whatever pivot you pick, is going to take n minus 1 comparisons. Like the max finding algorithm I said, it's always n minus 1, what is that average out, okay. Now, the second step where you are recursing is where some averaging happens, right. So, suppose the pivot happens to be ith smallest element, okay. So, yeah, this is what I want to compute. Yeah, suppose I called it R. So, let us use R, right. X is of rank R. That means there are exactly R elements smaller than X. Okay. Now, I am going to recurse, or and I am looking for kth smallest element, right. So, T of n okay. So, if R is equal to k or k minus 1, then T of n is what? N minus 1. That is all, right. What I want to do is for different values of, remember we are going to do averaging. So, different values of R, I have a performance measure of the running time, I will average over all that, augmented with the probability that R will take that value, okay. So, if R is k minus 1, there is nothing more to do except that first step and we are done, okay. If R is greater than k minus 1, what do I have to do? What is it? T of R, exactly, right, because I am going to recurse on the left side whose size is R. And if R is less than k minus 1, I am going to recurse on the right side, and what is its size? K minus R is the rank I am looking at, but what is the set in which I am going to recurse? N minus R. N minus R minus 1, right, because you ignore the X also. So, it is N minus R minus 1. So, you are going to recurse. So, is the picture clear? So, here is my list. I picked some X and I got S and L, and if X happens to be of rank exactly k minus 1, we are done. If X happens to be greater than k minus 1, then I am going to recurse in this side whose size is R. Otherwise, I recurse on this side whose size is N minus R minus 1. This is it. Now, I am going to do my entire averaging. Okay. So, the expected value of T of n, I will write a recurrence, I am not going to solve it, n minus 1 plus summation R equal to 0 to k minus 2, because if R is less than k minus 1, it is T of n minus R minus 1 plus, and if R is greater than k minus 1, so k to n okay, this is more or less correct. I am still missing one step. I want to see if anybody catches it. There is no averaging happening if I just write all of this, right. So, what is the probability that R is in this range? 1 by n. So, I just have to put this. Okay, so this is a proper analysis of the expected number of comparisons made by this algorithm. It looks pretty messy. How do I solve this recurrence relation? Well, it turns out one can show its order n, you can use induction. But I'll just give you some intuition about it. Okay, I'm not going to give a proof of this because it's just, I mean, you even need to know why do you think it's order n. I mean, once I tell you it's order n, you assume it is less than or equal to some c times n, and then apply induction because it's each term is some. Oh, by the way, I should put this expected, right? Because there are some random steps happening in each of the steps. So why do we even expect it to be order n? Let's just come back here. So first I said see what I said is what is happening here. I said even this, not I said, you all worked it out and said it's order n, right? What is happening is if I end up throwing away n over 4 elements after this first step, what is the purpose of the first step? Suppose it throws away a fraction of elements, that's good news. That gives me order n, because if it throws away 1 over 4 elements, n over 4 elements, then the recurrence would be something like this, which solves to order n. Okay. Yeah, this is also order n. It throws away n over 2 elements, so it's order n. What is bad is it didn't really throw a fraction of n, but it just removed one element and some constant number of elements, right? So that's the case where it's shooting up to n square. So now let's look at probability that the x you choose will throw away a fraction of elements, and I want to argue that that is a good probability. And that is the intuition for why you most of the time you will end up with this kind of a recurrence, right? This kind of a good recurrence and not the bad recurrence. So it gives you order n. Okay. So and that's very easy to argue, right? So I have this and my x, which I pick uniformly at random some element. And what is the probability that, let's say this is some rank n over 10 and this is rank 9n over 10. Okay, I hope you all understand what rank means, right? You take the sorted order, basically rank tells you how many elements are smaller than it. If an element has rank I, then I elements or I minus 1 elements are smaller than it. Okay. Now, if I just go and pick a random element from this list, what is the probability that it is in this range? Its rank is in this range n by 10 to 9n by 10. Okay. The element I pick uniformly at random, what do I know? I know that its rank can be anything between 1 and n uniformly at random. So, what is the probability that its rank is in the range n by 10 to 9n by 10? Yeah. So, it's a uniform, it's a random pivot, right? I'm picking a uniform element 1 to n. I'm told that that element has rank 1 with probability 1 by n, 2 with probability 1 by n, 3 with probability 1 by n, and so on. Okay. 5 by 4n. What is the total number of ranks? N. How many ranks are good ranks? 8n by 10 ranks are good ranks, because if I want it to be in this range, there are 8n by 10 ranks here. So 8n by 10 ranks are good range out of the n. So what is the probability? 8 by 10, 4 by 5, which is very good. So with 4 by 5 probability, the element I pick up will be in this range. Now let's come to second step. I do the partitioning. My kth smallest, I don't know what k is, but after that partitioning, either I am going to recurse on the left side or on the right side, right? Either way, some n over 10 elements are gone, right? If I partition and if I recurse on the left side, then this n over 10 elements will be gone. If I recurse on the right side, this n over 10 elements are gone, which is good recurrence. Remember, I said if a fraction is thrown, you have a linear time. Okay, so with probability 4 by 5, your running time is something like 10n, because if you do the work it out, it's some 10 times n, and you know, you can convert this into a nice, with what probability, I mean, you reduce this range, then you have a smaller probability, but the running time will increase. No, running time will decrease because you get to throw away a larger fraction of elements. Okay, so the whole thing, this whole recurrence is all about what fraction of elements you get to throw away, and there are a number of ranks in the good range. I mean, the probability that you are going to be at the very extreme, because that's what gives me n square running time, is so low that overall it turns out to be order n. Okay, that's sort of the intuition that would, so probability that x has rank in n over 10 to 9n over 10 is greater than or equal to, or is exactly equal to 4 by 5. That's good, much more than 50% probability. And when you do that, the recurrence turns out to be a good recurrence, because you end up throwing a fraction of the elements, and that's the intuition for why you get a linear time solution for this recurrence. But you really have to solve this, and solving this is just induction, right? So assume it's at most Cn, and then you do some calculations and you will realize that it works out fine. Okay, so I won't say much more. So the I said in 1970s, finding a median algorithm in linear time beating sorting was an important open problem, and this was the first algorithm discovered, the randomized algorithm. And later people figured out a way to find the deterministic pivot which actually throws away a fraction of the elements. Okay, that required more work afterwards. Okay, so this tells you that, you know, the analysis maybe is somewhat involved, but from the algorithm's point of view, it's simple, and it has a linear time expected performance. Okay, how much time I have? It's about 15 minutes, right? So maybe I'll quickly tell you about Quicksort. Again, many of you have seen Quicksort, may not have seen the analysis, but the analysis is very similar, so I will write the recurrence relation and we can come back to it. Or maybe we'll do Quicksort. Okay, so how many people have seen Quicksort? Okay, about half the people have seen. Okay, good. So it is very similar. So if I can write this as Quickselect. Okay, so let's call this as Quickselect. The big difference between Quickselect and Quicksort is that you will recurse on both sides. Quickselect, you are just going to recurse on one side. Okay, that's why it's linear, whereas Quicksort will be n log n on the average. right? So the algorithm pick a random pivot again. And partition into S and L, all those smaller than x, all those larger than x, and step 2, recursively sort that's all, right? 2 line essentially. Pick a random pivot, do your partitioning, and then once you have partitioned, sort this part recursively, this part recursively. In all these algorithms, there is a tail condition. If n is small, you do some brute force kind of thing. Okay, I am not writing those things down, but usually when you write a recursive algorithm, you should handle the small element case separately, and you say how to bail out of the recursion. Now let's analyze the algorithm. So if I write, so it's a random variable again. Why is it a random variable? It's a randomized algorithm. Where is the random step? The picking the pivot, right? Because based on that, your algorithm's performance varies. So if I say Tn is the number of comparisons performed, the expected value of T of n. First step, how many comparisons? We will put, yeah, how many? N minus 1, right? After that, because the size of S is a random variable, size of L is a random variable, so you recursively solve it and take the expectation and expected value of L. Okay. So again, let's look at some good and bad cases for S and L, right? What's a good case? Pivot is median, right? So then S and L will be how many? N by 2, right? So the good case is we have 2T of n by 2. Okay. So there is no expectation because I just said pivot is middle element, there is no randomness. Okay. So this again by master theorem or whatever you have seen solves to 2Tn by 2 plus n log n. Log n. Can you really sort in log n time? I mean, there is n steps already here. N log n. Right, this is exactly what merge sort does. Sorts the first half recursively, T of n by 2, sorts the second half recursively, T of n by 2, then it does the merging step in n minus 1 comparison. The bad case is first step is n minus 1. Yeah, what is the bad case? Tn minus 1, right? So suppose you pick the smallest element as a pivot, there is nothing on the left, everything on the right. So Tn minus 1, and which we already saw is order n square. Okay. So, now you can do something like what I did here, like this, right. Suppose the pivot I picked is of rank r, then what would be T of n? In the case, this is quick select, but for quick sort, suppose rank the pivot I picked is of rank r, then what would be the recurrence relation for? No, r is equal to, let us say it is r, it is r, there is no k here. Suppose I pick the pivot I picked happens to be the rth smallest element. There are r elements smaller than that. Now, what would be the recurrence? So, there is T of S, there is T of L, you have to recurse, right. Exactly. T of r plus T of n minus r minus 1 plus n minus 1. The only thing is I do not know r now. R can take all possible values with probability 1 over n. So, you put that 1 over n and do your analysis, right. So, let me just, in the interest of time, I am going to say expected value of T of n is equal to n minus 1 plus summation r T of r plus T of n minus r plus 1 with probability 1 over n, right. So, the difference with this and quick select, what is the difference? Both, we are recursing on both parts in quick sort. In quick select, we only recurse on one side. Okay. So, this, okay, I may be off at the boundary conditions here. This one can show is turns out to be order n log n. Okay. So, maybe I will give you a slightly so this is an exercise again by, this looks similar to the quick select recurrence. There is a difference because here the r goes all the way from 1 to n, whereas there going from 0 to k minus 2 something and then k to n something else. Okay, maybe I should put the expected value. Sorry, this is expected. But let me just give you slightly different proof, 5-10 minutes and then I will stop. One can write this recurrence relation very similar to quick select, solve it, use induction and show its n log n. But let us so if you see this quick sort, what does it do? It just partitions the element, right. So, you have these n elements, I pick some pivot and then I recursively some part of it goes to the left, some part of it goes to the right and it does this. It's like a tree and at the end of it you will have all single elements here when you get sorted. Okay. So, let xi be the ith smallest element. Now, what I want to compute is the following. What is the probability that xi and xj will be compared. In this whole quick sort, you have this random experiment which is based on the pivot. When you do this and finally finish the sorting, what I want to know is what is the probability, pick some pair of elements, let's say xi and xj, what is the probability that this pair will be compared in this algorithm, okay. But the thing about quick sort is that once you have partitioned it, an element on the left and an element on the right will never be compared, right, because you have done this. So, you sort this, that is it. You are not going to make a comparison between this and this. Okay, so, I want to know when will these two elements be compared. Okay, so, this is the ith smallest element. So, think of final sorted order is like this. One more thing, once an element is compared, it is never going to be compared again. Okay. So, now can you write, let us call this as some Rij, then what is expected number of comparisons? Can you tell me in terms of Rij? This whole quick sort experiment, picking a pivot, comparing it, partitioning it, and then picking a pivot, partitioning it, picking a pivot, partitioning. This is what is happening. At the end, there is some sorting complete. Now, I just say, let me pick the ith element and small jth element at the final sorted order. I want to know what is the probability they are compared. Let us call that as Rij. So, now what is the total number of comparisons on expectation? In terms of Rij, I mean, isn't Rij sort of capturing all comparisons? No, I am not, we will compute the probability Rij later, that is left. Once I finish that, I will be done. But can you tell me what is the expected number of comparisons in terms of Rij? You are all hungry for lunch. And isn't Rij for every Ij capture all the comparisons? So, I claim it is simply summation Rij. Because after all, in this whole algorithm, there are comparisons happening, and I am saying, hey, what is the probability that these two elements are compared? And that is, if they are compared, I add 1, otherwise 0, and I do it for every pair. That is the expected number of comparisons, right. So, now all I need to do is to compute Rij. So, let us again think about in this entire quick sort, when will a pair of elements be compared? When they end up in the same partition. Yeah, see, but at the end, everybody is in their own individual element. So, what do you mean by they end up in the same partition when? Yeah, so you are right. So, if they end up in different partitions, they will never be compared. True. So, they end up in the same partition when? And even if you are in the same partition, you may not be compared because, let us say there are 20 elements, they belong to the same partition, and somebody else became a pivot, and when you compare, they become part of different partitions, right. You have to be in the same partition throughout. When do you do this comparison? Okay. And notice that you always compare only with the pivot. So, here is a hint, right. The comparison is happening only with the pivot. Step 1 is the only place where you are doing comparisons. That's the same as saying they are in the same partition. Okay, but these elements also will become pivot, right? At the end of it, everybody becomes a pivot, and they are all in the single element. So, so let's look at xi plus 1 xj. At some point of time, let's say this is the list. Okay, xi and xj are in the same part. And now after the step, they may split. So what is the problem? When will you compare xi and xj? At this step, let's say this is, you have reached up to this point, they are all in the same part, xi and xj are together. Now, when will you compare xi and xj? Any of them? If any one of them is a pivot. Okay, but I told you everybody will be a pivot all the time. Okay, somewhere everybody will be pivot at some time, but what I am saying is that one of them must be a pivot before anybody else in this list becomes a pivot. That's the point. In this step, at this step, xi or xj must be pivot, because when you do this partitioning, if somebody else becomes a pivot, xi and xj will get split, and then they will never be compared. Okay, so at this step, xi or xj must be a pivot. Then xi and xj will be compared. Okay, so I'm going to write this. Rij equal to probability that xi or xj is a pivot before xi plus 1 xi become pivot. So meaning at this step, you are going to do this partitioning. You can even have more elements later, that's okay. I mean, there are more elements to the left, more elements to the right in your part. But if xi or xj is a pivot at this step, then xi and xj will be compared. Now, what is the probability of that happening? Well, you are doing a uniform random pivot. How many elements are there? There are j minus I plus 1 elements are there, out of which you are looking at 2 elements to be pivot. So, I am going to say that is 2 minus j minus I plus 1. Now, if I just go substitute this value here, it turns out okay, so maybe let me try completing that proof. So, summation I less than j. So, you see some sort of a harmonic series coming here now. Summation I going from 1 to n and j going from I plus 1 to n 2 by j minus I plus 1. This is equal to summation I equal to 1 to n. Let me take the 2 out and say this is going from I plus 1 to n. So, if it goes all the way from 1 to n, it will be Hn harmonic series. So, this is 2 n Hn, and Hn I told you is asymptotically order log n. So, this is okay. Yeah, so I may not have, you may not have followed all the details here, but compared to this humongous recurrence relation and trying to show that that is order n log n, this is a slightly different proof. I just pick some pair of elements, ith and jth smallest element, analyze the probability that they will be compared, and the probability again because of this pivot being random, and argue that that It's a one line argument, and with that you plug it into this and it gives you an order n log n proof. Okay, so what this randomization gives you is simpler algorithms, right? Particularly for selection, I told you. So from the practitioner's point of view, he or she has to just implement the algorithm and go away, right? I mean, it's a simpler algorithm, which is good. But we have to argue that it actually works in practice very well, and that's the complicated part, and that's where all these randomization probabilities come in, and we argue average case. So I wanted to do one more example, but we ran out of time. That's fine. So one other comment is that we only showed expected value is n log n for sorting and order n for that quick select, but you can also show tail bounds, right? Like what Arijit talked in the morning, where you can say that it's not just the average which is n log n, with very high probability it's n log n. Okay, so for most values of this pivot, not only at the initial step but every intermediate step, the overall running time turns out to be n log n. That's why quicksort is actually called quicksort. It works. Now, it's simple, works in practice, even though the worst case is n square. Okay. Similarly, quick select, and that tail bound argument requires some more analysis and more work. Okay. So we may or may not have time to do that. Okay.